These are the notes for section 9.6. You're going to need to have your textbooks open to page 567. We will be doing a little bit of graphing today, but I have drawn in all of the axes for you, so you will just need a couple different colored pens. So we've been talking a lot about graphs and what happens, and we've also been talking about functions, and today we're going to talk about exponential functions to be more specific. Now if you remember, an exponent is the number of times a base is used as a factor. So if I have x to the n power, n is the exponent, and it's the number of times I will multiply, or I will see x as a base being multiplied. Now, I have already filled in your vocabulary, so you should pause the video. I'll read through them. You should pause the video, fill them in, and then we'll keep going. So an exponent is the number of times x is used as a factor in the expression x to the nth power. So n is the number of times. A function is a relation in which each element of the domain has exactly one range. And so an exponential function is a function of the form y equals ab to the x power. A cannot equal 0, b has to be greater than 0, and b cannot be 1. So some examples of that are 2 times 3 to the x, 4 to the x, and 1/2 to the x. The reason that we put 1/2 on the inside of parentheses is because we don't want to have to worry about that fraction, because we don't want it just to be 1 to the x power or just 2 to the x power. We want the whole thing to the x power. Now we're going to talk about what those graphs look like. If you turn the page, you're going to graph y to the 3x. And this is a really good example. It's very basic. So the first thing you're going to do is you're going to start with a table that includes the y-intercept, where x is 0. So remember, the y-intercept is where it crosses the y-axis, and it's where x is always 0. And then the next thing you do is you choose points to the left and to the right of x equals 0, fill them in the function table, and then you'll draw in the curve. So what I'm going to do is I'm going to let x be 0, be kind of like my, it's not a vertex, but it's going to be my middle point. And then I'm going to choose to the left and to the right of it. Now when I drew in this table, I included the function rule, and then the output are the y values. So if I have 3 to the negative 2 power, remember that's the same thing as 1 over 3 to the positive 2, or 1/9. If I have 3 to the negative first power, that's the same thing as 1 over 3 to the positive first power, which is just 1/3. If I have 3 to the 0 power, anything to the 0 power is just 1. 3 to the first gives me 3, and 3 squared gives me 9. So now I have my ordered pairs. I have -2, 1/9, -1, 1/3, 0, 1, 1, 3, and 2, 9. Those are all my ordered pairs. I can draw them on my graph. So I'm going to start with 0, 1. So I have 0, 1, 1, 3, 2, 9, and then I'm going to go to the left because I'm getting into those tricky fractions. And I have 1/3 and 1/9. So notice I have this curve that gets closer and closer and closer to 0, but never quite touches it, and then it curves up really fast. Okay? And that's what your curve is going to look like. Don't forget to label your ordered pairs. So I have -2, 1/9, -1, 1/3, 0, 1, 1, 3, and 2, 9. Okay? Turn to the next page. Let's go ahead and graph another one. I'm going to go ahead and I'm going to make my t-chart. Now I have x, y equals 1/3 to the x power, and y. Now I'm going to include 0, and then I'm just going to include -2 and +2, and I'm just going to do those three because it'll give you a good enough picture of what's happening in that graph. So I'm going to start with 0, or actually let's just go ahead and start at the beginning. So I have 1/3 to the -2 power, which is actually just the same thing as 3 squared. So I get 9. And the reason it just becomes 3 squared is because remember, if I have to write this as 1 to the -2, 3 to the -2, and then I would move this to the top and this to the bottom, so I would get 3 squared, 1 squared, same thing. So I get 3 squared over 1, which is just 9. Then I have 1/3 to the 0 power. Anything to the 0 power is just 1. Then I have 1/3 squared, which is 1 squared over 3 squared, which just gives me 1/9. So I have -2, 9, 0, 1, and 2 to the 1/9 power. Or sorry, not to the 1/9 power, to 1/9. So my curve, see how now it's declining really fast, and then it slows down and it gets closer and closer to 0, but it never quite touches 0. Okay, if we label our points, we have -2, 9, 0, 1, and 2, 1/9. Okay, so that's that curve. Now, let's go to the next one. I have 1/2 to the x power minus 1. So remember when we were talking about parabolas and their translations, and we said when you subtract something, it moves it up or down? That's going to happen here. It's just going to take this kind of graph and move it down a little bit. So we'll start with our t-chart. And then we have x, 1/2 x minus 1, and y. I'm going to do 0, -2, and 2. So let's start here. We're going to have 1/2 to the -2nd power minus 1. And I'm going to rewrite that as 2 squared minus 1. So I get 4 minus 1, which gives me 3. 1/2 to the 0 power minus 1. So I get 1 minus 1, or 0. And then I have 1/2 squared minus 1. And that gives me 1/4 minus 1, which gives me -3/4. Okay, then I can start plotting my points. I'm going to say -2, 3, 0, 0, and 2, -3/4. Now, when we're talking about these ones, it would get closer and closer and closer to 0, but it would never touch it. But we've shifted this down 1, so instead of getting closer to 0 and never touching, it will get closer to -1 and never touch. So this gets really steep, and it kind of slows down, and it gets closer and closer to -1, but never quite touches it. So then I label my points. So those are what the exponential functions look like when you graph them. And fortunately, we can use those graphs to solve real-world problems. So this real-world problem can actually be found on page 568. It's example 3. And I'm not going to make you graph this one. I'm going to show you how to graph it on your calculator. And then we'll decide what we can use from that data. So, the problem reads, the consumption of soda has increased each year since the year 2000. The function c equals 179 times 1.029 t models the amount of soda consumed in the world. C is the amount consumed in billions of liters, and t is the number of years since the year 2000. So the first thing we're going to do is graph the function. This is the function that they're talking about. So I want you to pull out your calculator. And before we get started, we're going to change our window. So you need to go to Window. And I'm going to tell you that the dimensions are going to be -50, +50, 10, 0, 350, 25, and 1. Okay? Then you're going to go y equals, type in 179, parentheses, 1.029, end parentheses, and then raise it to the x power. Okay? Then click Graph, and this is what your graph will turn out to look like. Okay, so that's great. We have this, but what does that matter? Now, so that means what values of t, or x in our case on our graph, actually mean something. Now, we're talking about t being the number of years, so t is the x values. Can we have negative number of years? We're not worried about that. We're talking about years since 2000, so we're only worried about the right-hand side of the graph. And for t, that's what when they ask what values of t are meaningful. For t, remember that we're moving years since 2000, so when you get to 10, it means 2010. Okay? So now we have our graph. Now it's saying how much soda was consumed in the year 2005. To look at that, you can click second graph and it should take you to a table. Now the years since 2000 to get to 2005 are 5. So scroll down to 5 and it says 206.5. Now that was talking about the number of liters in billions. So we're going to say 206.5 billion liters. On your homework, you are going to be expected to have labels and include that billion part because that is important for when they're asking. If you had just put 206.5 liters, that wouldn't make any sense. So make sure you add in that billion. And you can't just leave this blank because they don't know, are you talking about gallons, are you talking about ounces, are you talking about cups? So you have to be specific. Okay? Now think back to when we were talking about linear equations and linear functions. That was at the beginning of this school year. And we know that they had a constant rate of change or a slope. Now take a look at our graph on our calculator. We can see that it's not changing at a constant rate of change. There's no line, so it's not rising and running the same amount every time. However, we can see that there's kind of a pattern to that curve. It's going to not have a constant rate of change, but it is going to have a constant ratio. And if you remember back, the definition of a ratio is the comparison of two units by division. So remember, we were comparing two numbers or two quantities by division. So let's take a look at this example. This gives us an exponential function. So if we were to graph these lines or this curve, we would see that it would give us an exponential curve on our graph. So they say look for the pattern. Up here, it's plus 5, plus 5, plus 5, plus 5, and plus 5. So that is changing constantly. Now let's come down here. It'd be minus 32, minus 16, minus 8, minus 4, minus 2. Now notice these are decreasing by the same ratio as from one to the next. And what they're doing is, see how these are the same? They're just cutting it in half. So they're saying times 1/2, times 1/2, times 1/2, times 1/2, times 1/2. So the constant ratio is 1/2. Or we're going to say, instead of constant ratio, we're going to say common factor of 1/2. Okay? So they ask us to graph this data using the list on our calculator. What that means is you need to go second stat. Oops, that's not what I want to do. Go to stat. Okay, so we're going to say go to stat, click edit. We're going to clear out list 1, so we're going to say we want list 1 to be 0, 5, 10, 15, 20, 25. Okay? Go over to the second list, and this is going to be 64, 32, 16, 8, 4, and 2. If you have any extra things, you need to go ahead and delete them out. Okay, so now when we go to graph them, we should just be able to click, let's see. Let me think about that. So what you need to do is you need to go up and you need to click second y equals, and it's going to take you to stat plots. Plot 1 needs to be turned on. The type needs to be the second one. Okay? X list should be L1, Y list should be L2, and I want your mark to be the first one on the left, so the open circle. And then click graph, and you will see that we have an exponential curve. Now they didn't extend those curves, but if you can see how it slows down and gets closer and closer and closer to 0, but never quite touches it. go to the next page. It asks us to determine whether the set of data shown displays exponential behavior. The only thing you have to do is look for numbers that add the same on the x values, and then you look for a common ratio here. Okay? So, this is plus 3, plus 3, plus 3, plus 3, plus 3. So that one works out for us. Now let's come down here. This one's plus 4, plus 4, plus 4, plus 4, plus 4. Now, that would work if we were talking about sequences or an arithmetic thing, or a line, because it's changing the same here by addition and the same here by addition. So this would give us a linear function, but it doesn't say I can multiply this by a number and multiply all of these by that same number and get my pattern. So no, this is not an exponential function. Okay? The only way we could have said yes is if we had been able to multiply this bottom row by the same number and get our resulting elements. So that's the end of the 9-6 notes. Let me know if you have any questions.